Swayam Prabha. Digital India. Educated India.
So, in today's class we will solve a few problems which exploit the view factor algebra, and to the extent possible we will try to obtain all the view factors in a n surface enclosure system by using view factor algebra itself. Towards the end of the class maybe we will work out one problem in which we have to use the double integral. Okay, it is not actually double integral, but double integral over ai aj to in order that you are able to appreciate how we can use this fundamental formula to derive view factors. So, in yesterday's class we looked at the triangular enclosure problem where there was a general triangle with A not equal to B not equal to C. Okay, the line segments are given as A, B, C. This duct is infinitely deep in the direction perpendicular to the plane of the board. Maybe at this point I did not emphasize in the previous class, so a lot of people had doubt whether it is having a finite depth in the direction perpendicular to the plane of the board. So, it is implicit that we are looking at a 2-dimensional geometry. So, we are not worried about the depth direction. The depth direction is much longer compared to the other dimensions. It is okay for you to assume unit depth. Therefore, the area of this surface we can say it as b into 1. Okay, so that is why I put it as b meter square per meter depth. That is the way people will say, right. Surface area of a pipe is also said as so many meter square per meter length of the pipe. So that it is consistent. Okay. Now I start solving this problem by first writing the 3 summation or sum rules. I apply the sum rule for the surface A, f of A to A plus f of A to B plus f of A to C equal to 1. It is a plane surface, therefore f A equal to 0. By the same token I can write down the summation rules for surface B as well as for surface 3. So, totally correct 3. Okay. So, there is no need to work out any view factor based on integral ai integral aj cos theta I cos theta j dai daj divided by pi r squared whole thing multiplied by 1 by ai. There is no need to do that. Okay, fine. Now we are at this stage. You can call this as 1, 2, 3. In fact, you can start with this. You can start with this as the preamble to the problem. You can start off the problem by saying how many total number of how many view factors are there in total, how many sum rules, how many view factor relations are available for you to exploit. So that 9 n square minus finally we arrived at a number 0. Therefore, integration formula is not required. Then once you are convinced, then you know that somehow you have to algebraically manipulate all the view factor relations to get the view factors. Okay. Now I will erase this, I will keep this. Okay. So Okay. Now what I do is now I do 4 plus 5 minus 6. Now I can exploit the use of color chalks. Okay. So what I am going to do is exploit the availability of color. Okay. Which other fellow will go? BFBC, right? Right? Whatever is indicated in red color is the same, and we are subtracting one red from the other red. We are also subtracting one blue from the other blue, right? So what remains? Equation 7 is do that, you get so this is nothing but suppose I have a V groove. Suppose I have a groove, right? So for example, I have a surface. So this is 1 and this is 2. Yeah. So here there is vacuum, it is radiating and all that. I am interested in getting F12. Okay. So in order to make it so that you are able to follow what I am saying, let us say this is L, this is also L. I will call this as a wedge. Okay, this is a wedge. In English we keep saying, no, don't drive a wedge between the two people. Okay, so this is a typical wedge. Now the included angle is alpha. Problem 18, get F12. The question clear? It follows from problem 17. Okay. So if you want back side, there is no activity. Okay, on the back side there is no activity. Please remember, we are using enclosure theory. Therefore, what is the first step in technology? Put a dotted line and close this fellow and make him a triangular enclosure. Okay, let us use a green color chalk. We can make him 3 if we want. It's not required. So Vikram, got it? What is it? 1 minus? Huh?
Sin alpha by 2.
1 minus sin alpha by 2. How many of you got it? What happened? Got it? Finished doing it? You know, why don't you do it? Oh, you came late. Okay, complete the. Come see what happened. You are able to see from there? So I will put a dotted line here. What is this fellow? This is alpha by 2, na? What is sin alpha by 2? Sin of alpha by 2 is this by hypotenuse, right? Okay, therefore this will be L sin alpha by 2. Which one? This one. What about this fellow also? So the length of the side 3 is 2L sin alpha by 2. Okay, F12 okay, I am saying length of first surface and L okay. As an engineer, how will you validate this result? You have to be smart, you should be accurate. As an engineer, alpha equal to 60. What? Alpha is equal to 180. Very good. Alpha is equal to 180 means the wedge is like this. The wedge will open like this. This fellow and this fellow are not seeing each other. So when alpha is equal to 180, there is no interaction between them. Okay. Therefore, sin alpha by 2 will be sin 90, that will be 1, 1 minus 1, it is 0. Okay. So this wedge is an important surface, it is an important configuration which is useful in radiative heat transfer. Okay. Where can I tell you some places? Okay, one possibility could be like this. Suppose you have a hot fluid, okay, and you have got fins. This can be used in both terrestrial applications as well as in outer space. These fins need not be of a constant area fin, you can have a trapezoidal fin. Then if you look at this configuration, it will be like a wedge in between, right. Then you have to consider the view factors, and if you want to solve the combined convection radiation problem, it is very involved. 10-15 years back we were giving this as MS projects, MTech projects, but not any longer. Are you able to understand? So we will use different profiles, different fin heights, different thicknesses, we will optimize what is optimum fin configuration, what material, or if the material is fixed, geometric optimization. Okay, when we do geometric optimization, if inside if there is convection, if you pump with more velocity, then heat transfer coefficient is more heat dissipation is there by the fin, but the pumping power also increases. Therefore, the entropy generation increases because of pumping power, but the entropy generation due to heat transfer decreases because more heat is transferred at the same temperature difference. Therefore, if you look at the overall entropy generation, whether it reaches a maximum or minimum, is there a configuration for minimum total entropy generation? Okay. This what I have just explained to you is a 2-minute course on a very important topic called EGM, entropy generation minimization. That is a well established field by itself. Professor Bejan has written a book on entropy generation minimization. Okay. So there are umpteen ways of optimizing. One, see, your optimization in heat transfer does not always mean that you want to maximize the heat transfer, right. Sometimes you also want to minimize the pumping power, or you want to have a trade off. Okay. So we will stop it at that stage. Now there are two concentric pipes. Okay, there are two concentric pipes. There is a pipe inside which is carrying a fluid. Okay, that is enclosed by an outer pipe. Okay. So, the inner radius is r1, the outer radius is r2, infinitely okay. Do not worry about the radiation activity on the outside of surface 2, do not worry about the radiation activity on the inside of surface 1. Problem 19, for the cylindrical duct, get all view factors. Assume that there is vacuum in between 1 and 2. Okay. This is one way of insulation. Okay. You can either have a flowing fluid or sphere within a sphere. It can be used for transporting liquid nitrogen, liquid oxygen and all that. When they transported over large distances, the temperatures will be 150 or 160 Kelvin. Outside you will have 300 Kelvin, there will be heat leak. Because of heat leak, what will happen to the liquid nitrogen? It will vaporize. So, you have a small vent, allow this thing to, so you can actually work out the radiative heat transfer and find out, because of the radiative heat transfer, m dot into HFG, what will be the rate of vaporization of this. Then I will give given a time of 2 hours or 3 hours, initially if you have 100 kg of liquid nitrogen, how many kg of liquid nitrogen will be left at the end of the exercise. These are a practical problem, are you getting the point? So, the starting point for the analysis is the view factor. R1 plus R2, no. Very good. Get all VFs. How many view factors are there? No. VF matrix. Okay. Then when we do the enclosure theory, I will give you epsilon 1, epsilon 2, T1 and T2, then you will do the analysis, that comes later. First view factor. Now F11, because it is a convex, 1 is a convex surface but 2 is a concave surface. Okay. F12, 1, A1, okay. So 19, problem number 20, repeat the procedure for concentric spheres. A1 by A2 remains R squared, very good. F21 is R1 squared by R2 squared. I have given the VF matrices in 2 different colors. fine. Okay. Please remember that we will revisit all these problems when we actually solve the radiation heat transfer between these surfaces. The first step we are looking only at the geometry, okay. Enclosure theory I will teach you next Tuesday's class, okay. So something is implied. Let's escalate the complexity level now. I have a quadrilateral enclosure. Okay, so can you do like this? No, doesn't work out. This is difficult. What do you want to do? I want to put it as ABCD, man. Okay. Length is also, D is the length as well as the it qualifies the surface, okay. Everybody is through with this. What is FAC? Huh? What about FAD? Come on. Not so easy. Huh? How many independent view factors have to be determined? Okay, total UFs, total. Okay, some rules. Reciprocal rules. NC2 4 into 3 by 2 6. Self view factor. So total is 4 plus 6 plus 4 14. So number of view factors to be independently determined 2. But what are these 2? It's FA to C and FB to D. If you get FA to C, that same formula can be used. So now you have to crack, if you want to crack this problem, then you have to get this, you have to somehow get the FA to C, okay. Now and by symmetry or by analogy you can say that if you have got FAC, you also get FBD. So what is FAC, right? We have to start somewhere. What is the first step in technology? Very good. In order to make it in 2 triangles, what should you do first? Draw the diagonals. Very good. Just draw the 2 diagonals. Which triangle you want to take? Like this? Okay. Yeah, now how do you proceed? Yeah, please tell me. F, can you want to label the diagonals? You want to do that? Is it required? Okay, let us say that okay. One, think, got it? 1 minus triangular enclosure, wedge, trapezoidal duct, pentagonal duct. I am just looking at the list of problems I have to solve today. Huh? That you already studied somewhere. You derive. You have to derive. Next. Okay. Now, I think it is better to, you want to name the diagonals L1, L2? Okay. I think we should have placed the vertices as, we should have named them as okay, that does not matter. L1, L2, 1 is okay, L1, L2, L1 is enough. Now tell me, so FAC is 1 minus F, this is correct? FAA plus F, this is correct, right? Now FAB can be written as FAB is equal to A plus B minus L1 by 2A. FAD A plus D 2A. Now we will substitute FAC equal to 1 minus to A plus okay. So, for a general quadrilateral enclosure, this is the formula for, okay. This is called the Hotell's cross string method. So, if you have the, look at this in a quadrilateral enclosure, if you have two surfaces like this, the view factor between the two surfaces is equal to the sum of the crossed strings, that is L1 plus L2 minus the sum of the uncrossed strings divided by 2 times the line segment. That is why it is called the Hotell's crossed string. The string need not be there, it is an imaginary string, okay. Okay. So, FAC sum of crossed strings. It is a very powerful expression for 2D enclosures, okay. It lets you calculate for 2D enclosure any geometry, you can exploit this expression, and okay. Now let us, yes.
Aren't we changing the situation, physical situation, because we are changing the enclosure itself?
No, but if you look at energy balance, what will the sum of f a to a plus a to b plus f a to the a to this must be 0. So from here whatever is going to C and D must come through this imaginary L1. I mean there is nothing wrong in that, that is the energy balance. He has a valid point. Did you understand? Are we doing something by putting this L1 L2 is saying, but as far as I am concerned, the energy which is falling on C and D has to come from this, that is what I am saying. So it is okay for me to assume that. Is it okay? Now let us twist it little more. Let us take a pentagonal duct. So we did triangle, then we did quadrilateral. Now problem number 22. So problem number 22, I will A okay, get F12. Huh? Regular pentagonal duct. All sides are equal. I can give hexagonal duct, dodecagonal duct and so on in the exam. Hexagonal duct is used, you have hexagonal bolt and hexagonal duct can be used, okay. It is easy to make. So what is F1 to 2? What did I write here? F1 to 2 is FAC to, okay. Now you have to, what you have to do here is basically you must remember your math. Basically you must remember the included angle, you must know. What is included angle? 108, because this will be what is this? So what is called exterior angle? Exterior angle. Okay. So the exterior angle for a pentagon is 360 by n is 572 108. Is it, or what is it? Is that correct? Exterior angle is 360 by n 72, therefore the interior angle is 108. Each of this fellow is 108. Now if I join this, each of these angles is We do not know. Huh? Will it be 36? It will be equal only, it will be 36. Okay. Now, this angle. Okay, so what is this? 108. What is this? It is isosceles triangle, man. So 36. This is 36. Okay. Now this is 108. So this is 36. This 36. If this is 36, this is 36. This is also 36. Same story here. Okay. Ketan, you are not happy that all were 36, but unfortunately that is correct. Okay. Now, Vinay, got it? Answer F12 equal to? Huh? Sin 54 minus half. Huh? I don't know. I got 0.31. What is the answer? Right, correct. 0.309 is the right answer. Now we will do it. Did you use this Hortel's cross string? Yes, correct. So you have to use the Hortel's cross string. That's why I gave this problem after the Hortel's cross string. Now we will have to F12 is equal to. So what is F12? How did he start out this problem? F12 equal to, or did he say F12 plus, what did I write? F12 is equal to F, why did I do this? FAE to CD, yeah? Correct? FAE to CD. Now, I am confusing my terminology, does not matter. Now F12 so F12 is equal to AD, F12 equal to AD plus CE minus AC plus, very good, by, very good. What did I do? So F1 to 2 is sum of cross strings minus sum of uncrossed strings divided by 2 times okay. Now what are these values? What is AD? AD and AD AC will get cancelled. Okay. So what is CE? Huh? 2. Okay. What is sin 54? 1 point. Okay. Okay. So DE is L. Okay. Okay. So we can have next level of complexity will be hexagonal duct and so on. Okay. So we will close the discussion for the day with one more simple problem, and tomorrow's class we will do more problems on view factors. Okay. I will just close the discussion with a simple problem. Is everybody through with this? Okay. Let us consider another situation. So there is a circular duct. There is a circular duct. Do not worry about the radiation activity inside. It is R1. Okay. Now it is closed by another concentric cylinder, but unfortunately the other one is only half. So please get all view factors. Get all view factors. So what is the first step? Close it, very good. Close the bottom, the dotted line, and you will call him 3, huh? Okay, if you want you can call that fellow 3. What is F11? Okay. F12, huh? No, F1, 0.5, F13, very good, because the symmetry is there, right? So F11, F12 equal to F13. Why? By symmetry, correct? It has no special preference. Okay? Are you getting the point? Therefore, suppose I make this fellow up to 3/4 and leave, then the area ratio, other things will come. Okay. Now this fellow is not like this. Okay. Now what about F? What about F33? F33. Yeah. What is F22? Are you able to get the other things? Are you able to get the other things? So F11 is equal to 0, F12 equal to 0.5, F13 equal to 0.5. Okay. A1 F12, A2 F21. Therefore F21 equal to what is it? R1 by R2. Oh. F21 is also the same as F31? Yes. Huh? Tell me correctly. No, some half is there, no?
Half will come, sir. Half area and half the value.
Why half the value? For one it is full, isn't it?
0.5 into 2 by R1 and the other
Okay, what is the final answer?
R1 by R2.
R1 by R2. Okay. F21 equal to F31 equal to R1 by R2. Is it correct?
Yes.
Okay. And then F22. What I have done is, got it as R1 by R2, okay. So it depends on, I have given R1 by R2 equal to half or something, right. So what are the other things required now? What is F22? what about F23? F23. Okay, I think it's everybody is stuck or what? Obviously this problem can be solved, isn't it? It's a simple problem. Why are you getting stuck? Okay, so we'll stop here. It's 9:50. So we'll work this problem out in tomorrow's class. Tomorrow we'll also do some integration. I also give you a chart. What will be the view factor between two rectangles when you have got finite areas, 2D rectangles and all that.